everyone. Say hello because I've got a hello slide, so I can do my hellos properly. So this is me in the corner there. That's me about 10 years ago, when I can still remember how to shave. Things moved on since then. I'm based in Edinburgh, in Scotland, where I sort of live and work, independent consultant. Also run the Java user group there, which is sleeping, but will shortly awaken. And about 10 years ago, about the same time this photo was taken, I created a thing called PiTest, or PiT, which we're talking about a bit today. So that's my hello slide. There's some things missing from it, because things that people really shouldn't know about, at least not the people who are meant to employ me. So I don't mention here that I'm actually really quite lazy. I can put quite a lot of work into not doing work. I'm good at it. Also, fairly incompetent. I make a lot of mistakes. So I'm lazy and I'm incompetent, but despite that, I've been gainfully employed for the past 20 years as a developer, and people seem actually quite happy with my work. So there's a secret to this, and about 3/4 of the way through this, I will share my secret with you. You have to sit through the rest of it first to get the secret. That's the payoff. So let's kick on. So that was me. I also quite like to know who's in the room. So show of hands, who here self-identifies as some sort of developer? Most of you. Some sort of QA sort of person? Something else? Okay. And out of interest, of the developers, and the QA as well, how many of you work with Java? Okay, good portion. So you guys are going to be sort of well catered for. It's quite a lot of Java in the talk, but it's all kind of does apply to other languages as well. We'll get to that at the end. And finally, of the people here, who, like me, is quite lazy? Okay, a lot of you. And for those of you who didn't put your hands up, who of you were lying? Thank you. Right, let's kick off. Let's actually start with some questions, such as, how do I safely refactor my tests? How do I know if I can trust a test suite that I inherited? How do I ensure that I'm writing effective tests? Tests are sort of strong and good. How do I know if my team's writing effective tests? Which is really, if you think about just one question expressed several different ways, which is, how do I assess the quality of a test suite? Now, I've been to a few conferences now. I've asked the audience for their answers on this, and I've sort of collected them, written them all down, and there's some common themes that sort of come up. So, common answers, that's QA's problem. I'm a developer, I'm okay with that, because that's the least work for me. I'm a ninja rock star. I know my tests are good. It's depressingly common. There's better answers as well. They're not all terrible. I'm sure had I asked this audience, they'd all been good answers, but I'm in a rush. I do TDD. I know my tests are good. This is a better answer. It's better than I'm a ninja rock star, but it's not perfect. Because are you sure? So TDD is a process implemented by human beings. And even if you're not lazy, you're still infallible. You make mistakes. We all do. So you might think you've done your TDD process perfectly, but have you? You don't know. And even if you are perfect and apply TDD perfectly, what about your teammates? Are they perfect as well? Does everyone in your team also do this perfectly? And even if you and your team are all perfect and do this TDD perfectly every time, what about that sort of question before? How do you change your tests? TDD gives you a good solution to changing your code, but how do you refactor your tests? Do you write tests for your tests? And if you do you write tests for your tests for your tests? Now, I'm not sure how that ends. I don't think it ends well if it ends at all. Another good answer is peer review. It's good, but it's inconsistent. It depends on who does the review. It depends on have they had a good day, have they had coffee, a bad night the night before, all sorts of factors. It's labor intensive. It takes someone an appreciable amount of time in order to review some code. It's also a slow form of feedback. If you do it the traditional way, you write a bunch of code, and then towards the end somewhere, you do a review and realize it's all wrong, go back and rework. You're getting the feedback quite late in the cycle. If you do pair programming, it's not another form of peer review, that last problem is solved, the first two remain. And another common answer is code coverage. And when people say code coverage, they usually mean line, branch, or statement. There's actually loads more out there. There's data, path, modified, all sorts of exotic things I actually don't know all that much about, apart from the fact that very few people use them. But it doesn't actually matter, because none of these code coverage measures, even these exotic ones which I know nothing about, actually tell you anything about which bits of your code have been tested. It's not useless. It does tell you something, something useful, but it's not which code is tested. It tells you this. Given this lovely class here, this is some of my code, we can see that at least one test has executed that line. At least one test has executed this line, and no test at all have executed that line of code. And this is all it tells us. And unfortunately, executing code and testing code are not the same thing. You have to execute code to test it, you can't avoid it, but just because you've executed it does not therefore logically follow that you have therefore tested it. Because you might have tests like this. Now this sort of test actually is quite rare. This is what I call a bad faith test. Here, a team has been given probably a metric to meet. They've been told to get 70, 80, 90, 100% line coverage. They said, why? Well, just do it. So, okay, we've done it. We've written a test. It executes the code. The number's gone up. It provides no value, or very little value. It'd be very hard for this test to actually fail. Now, this is actually, I've seen tests like this. They do happen. Not usually with quite such an honest name, but they're quite rare. Most people writing tests at least have an attempt to write a useful test, or they're trying their best. So that's a bad faith test. Most tests are good faith, but still they can be deficient. So here we've got some more very useful code. We have this foo function here. It takes a Boolean, it returns a string, and someone's come along, I'm going to guess after the fact, after the code's been written, and said, okay, what's it do? Boolean in, string out. There we are, test case. We've got an assertion now, it can fail. Another test case, asserting, we've written a useful test. And it's not without any value at all, but what I'm guessing is the most important part of this function here, this call, isn't actually verified at all. There'll be full line coverage, probably full branch coverage, but no meaningful testing of the most important bit of the function. So code coverage tells you something, but all it tells you is what has not been tested. So these answers, they're not that great. Now, way back in 1971, a student called Richard Lipton came up with a much better answer to these questions. This is actually decades before most people were writing unit tests, at least as we understand them today. So he wrote a student paper entitled Fault Diagnosis of Computer Programs. And it contained a very simple idea, which was, if you want to know if your test suite tests some code, introduce a bug, and then see if your test suite can find it. It's pretty obvious when someone said it out. It's not a radically clever idea, but it's a very powerful idea. So here's a bug. Can anyone see it? You need memory and a close eye for detail. Two things I personally don't have, so I wrote it down. So we've changed greater than equal to greater than from that code from before. Here's a test suite. This is that bad faith test from before, split out into some actual test cases with assertions. We throw it in 0, 11, and 9. Quick show of hands. Have we tested the code? Yes. No. Okay, I feel there's some sort of big third category here we haven't sort of covered. Well, the answer is no, we haven't. Our test still pass because our suite is deficient. We're missing a test here right on the boundary of what happens at 10. So, just a bit of sort of terminology now. A change that's one we just saw when we've switched a greater than equal to greater than is a mutation operator. Loads of these things are possible. We go this way, that way, this way. We're not limited to conditional statements. We could take one method, call that, and just get rid of it. We could switch it for another, change zeros to ones. Really, any sort of small change to the code you can imagine could be a mutation testing operator. It might not be a good one, but it could be one. Etc., etc. Lots of possibilities. And when we apply one of these operators to some code, we create a mutant. And we can create lots of these mutants, and we can do it automatically. So, create a mutant, we run the test suite against it. If no tests at all fail, we say that mutant survived. If at least one test fails, we say that mutant was killed. Important take-home here, killing is good. Within certain bounded context, but yes, it's a... But what about this? We can mutate it. It's our same change as before. But there's a problem here. It's not always instantly obvious, but if you think about it, it still behaves the same. So what we're doing before is we're passing in this int. We've got a bit of state stored up here of the lowest thing we've encountered. And if it's less than or equal to, we store it. Or if it's less than, we store it. Either way, it's the same result. So these are logically equivalent sort of behavior, but expressed slightly differently. So it isn't possible to write a test that will kill that mutant. Any test you wrote which failed for that mutated code would also fail for the unmutated code. So we call this an equivalent mutation. Now, for years, these were considered to be a really big problem with mutation testing, because although you can, as a human, see, okay, that's logically equivalent, as a general algorithm, trying to automate it, it's not possible. You might be able to find some special cases, you might be able to find some heuristics that say this is probably equivalent, but in the general case, you can't say this is definitely an equivalent mutant, and this one here lacks a test case. We'll talk a lot more about equivalent mutants a bit later on. So this means that mutation testing highlights code which definitely is tested, as opposed to code coverage which shows code which definitely is not tested. It's almost like opposites in a way. It gives a really high degree of confidence in a test suite. Effectively, test your tests. And this I'm going to keep emphasizing again and again because it's the only technique I know which lets you do this. Nothing else out there gives you a way to test your tests. It's mutation testing is the only game in town. Which means you can now refactor your tests without risk, without fear. And the same way you can refactor your code. So hopefully I've already convinced you it's quite a good idea. So what happened to it? So in 1971 we had Lipton's paper. Just 9 short years later, the first automated tool. This breakneck pace continued into the 80s. Stuff actually was happening in the 80s. So research started to happen into mutation testing. Happened a bit in the 70s, but sort of picked up in the 80s. Didn't involve Mr. Lipton. He went on to do amazing things in computer science. I think he founded DNA computing. But other people picked up the idea of mutation testing and studied it. And one of the first sort of questions they asked was, okay, this sounds great. So we can see if our test can find these artificial bugs. Does that mean it can find real bugs? So to sort of think about this, they come up with 2 hypotheses. The first one was called the competent programmer hypothesis, which basically states that programmers are generally competent enough to produce code that's almost right. So you're typing away as a programmer, you're perfect, but occasionally a little typo, a little mistake. So programmers are basically competent, but make small errors. Your mileage may vary a bit here. And mutation testing introduces small changes to the code, so they look like these typos that our competent programmers are producing. Now, I think the big problem with this hypothesis is it's clearly completely wrong. I make bugs all the time. Some of them are little typos, others are big, huge, whopping bugs of great complexity, which are very hard to describe, yet alone understand. So my bugs don't all look like that. Some do, a lot don't. But that's okay. We have a second hypothesis that kicks in called the coupling effect. What this basically says is, if you've got a test that can find a little tiny bug in an area of code, the same test will find a whopping great complex bug in the same location. Or, other bugs apart from your small bug at the same place. Now this actually has quite good empirical report. There's lots of support, been lots of studies, they've taken real code bases, looked at real bugs, and all sorts of different things, lots of studies, and generally, not unanimously, but generally they agree that actually this is the case. Tests that find little tiny bugs will find more complex bugs at the same location. I want these out now. But it's important to understand this is a probabilistic statement. It's not like some mathematical truth. It's not that this can be proven that this is always the case. It's just something which generally happens in practice. And importantly, you will find counterexamples. You can't rely on this, but it's just generally true. Which means that if your test can find mutants, they will probably find real bugs. Through into the 90s. A few more academic tools came out. As we reached 2000. Now, 2000 was an interesting year for mutation testing because of this, a tool called Jester. Now, what's interesting about Jester isn't what it did. It doesn't think it did anything particularly new or different. It's where it came from. This was the first tool I'm aware of that came from the sort of open source community. All the previous tools have been research tools at universities. This is the first time someone said, this is an interesting idea, let's try and make a tool for people to use. Now, Kent Beck quite liked it. I'll read this out in full. Why just think your tests are good when you can know for sure? Sometimes Jester tells me my tests are airtight, but sometimes the changes it finds come as a bolt out of the blue. Highly recommended. Here we have Kent Beck the year 2000, giving it a ring endorsement for mutation testing and Jester. What do we think happened? Nobody used it. And we'll find out why in a moment or two. Into the noughties, lots more research papers, and we find ourselves in 2019. Now, I have a lot of problems with 2019. There's some things fundamentally wrong with 2019, which I'm not happy about. But in terms of mutation testing, it's actually quite good. It's in daily use all over the world. People keep talking about it at conferences, and not just me, which is great. It's using high-profile projects. Who knows what this is? Anyone? Shout out. The Large Hadron Collider. Apparently, it control systems are written in Java and mutation tested with PiTest. This one, I'll spare the pain here, is called Norway, which is not mutation tested, but its parliamentary election systems were. Again, written in Java, or bits of it were, tested with PiTest, I think now been decommissioned, but still exciting sort of stuff. But those are the big high-profile projects, like sort of safety-critical kind of things, but mainly it's used for normal code, the stuff that I write. We're talking tractor websites, recruitment things, insurance, lots of banking, biotech and media, just day-to-day, non-safety critical code. So, what happened? We had 40 years of research, which suggested this wasn't going to work. There were two fundamental problems. Firstly, it was too slow, which we'll get to in a second. And secondly, that equivalent mutant problem I mentioned earlier. We'll get to that later on still. Let's look at too slow first. So, if you think it through, what to make these mutants, you have to compile the code. You change the code, you compile the code, you make your mutant. Got 1,000 mutants, that's 1,000 compile cycles. You should run the test suite. Every mutant, you have to run all the tests, see if they fail. 1,000 mutants, that's 1,000 test runs. And that can add up. If you take a look at GOTO Time, this is a Java library, in fact, a small Java library for dealing with dates and times. It's about 68,000 lines of code, about 70,000 lines of test code. It takes about 10 seconds to compile on my previous laptop at least, about 16 seconds to run the tests. Now, my maths is a bit sketchy, but I wrote this down beforehand so we wouldn't get it wrong. If you had 10,000 mutants, that's that number plus that number, which is that number, which apparently is 72 hours, which apparently is about 3 days. So we have a small library which is going to take us 3 days to mutation test. You can see why no one did this. It's wildly, wildly impractical. In theory, it is, anyway. Now, I didn't understand this. I hadn't read about this stuff. I didn't know this. No one had told me this. So not knowing that it couldn't work, I tried to build a tool that would do it. I said my maths is a bit sketchy. I never did the maths to start up. I mentioned before, it's called PiTest, or also known as PIT, for reasons that are not that important. And I think I'm going to rather inadvisably now do a live demo. So let's see what happens. So we're going to demo on a thing called Truth. This is a tiny library from Google for doing assertions. It replaces things like AssertJ or Hamcrest, if you know those. It's only 3,000 lines of code. It's about 3 seconds to compile the thing. So we're talking really, really quite small. About 7 seconds to run the tests. It's actually quite well tested. It's got 90% line coverage, which is not bad. So let's imagine we generated a fairly modest 700 mutants. Not even into thousands here, just the hundreds. I did the maths earlier. I'm told it takes about 2 hours. So I think we've got 30 minutes left. This should be a fun demo. Let's go try it. Right, there's bigger. So this is bound. So PiTest has a Maven plugin. I've just bound it to a profile called PiTest. I've misspelled test. Off we go. Talk among yourselves. That's just Maven running the test. This is now PiTest kicking in. It's doing some things. It's doing them still. Nice weather we're having. It's, actually, 55 mutation test units, which is like basically a unit of computation, which it uses. It packages things up together. So interesting behind it to do with static state and things, trying to limit them. But yeah, well, not time for that. Going through, this is just some things actually which the test suite from Truth was producing. And there we are. It's finished in, I think, a little less than 2 hours. I wasn't timing too closely, but a touch faster. So that was 37 seconds, apparently. I haven't got time to go through all the output here, but just know we've got some interesting summary information about things that have happened. The more useful stuff, though, is not here, it's in the report it spits out. And if you can hear, my laptop battery fan is going slightly wild from that. But okay, so this is slightly old school reports that PiTest spits out. I think they're due a bit of modernisation. But we see a mixture of line coverage and mutation coverage. That's just the ratio of how many mutants you generated, how many were killed. So apparently I'm going to look at abstract verb. I already know there's nothing interested in here, but just going to show you what the report looks like. So these big, long green lines here, this is just bog standard line coverage. These slightly darker areas here with a number next to them are where we've had one or more mutants generated and they have been killed. If you hover here, we'll see what we did is, I can't control my mouse. So we've negated a conditional. If you look in there, we have a not equal to, and we change it to an equal to. And separately, we've just replaced the entire return value with null. So effectively, we've commented out all this code, and also we changed this statement here. It's not that surprising that these mutants were killed. If you turn null from something, that's pretty easy to kill in a test. Anything you do at all assertion-wise is going to catch that. So not very interesting. And some more uninteresting results further down. Here we have this big, long line of red. This is no line coverage. And this sort of superimposed shorter bit of red, saying we had one or more mutants here which survived. And in this case, I think we've just taken out a method call to fail, so we've removed effectively the whole line again. Not surprising this mutant survived because there was no line coverage. How are we doing for time? Let's very quickly look in here as well. And a slightly more interesting result, but not much more interesting. Again, big long line of green, line coverage, red over the top. So we have a test that's executed this code, but the mutant has survived. So, okay, more interesting result. And in this case, we've again negated a conditional. But if you look a bit closer, it's still not that surprising because we can see that we had no line coverage inside this branch. So we had line coverage but not branch coverage. Mutant survived. It's not a big surprise. A bit later on, we'll see some actually interesting results from truth. But first of all, why didn't that take 2 hours? Lots of reasons. So first of all, it runs in parallel. So these days, everyone's got at least 2 cores. So 2 cores equals half the time. So we're expecting it to be about an hour, roughly, of execution. More importantly, no compilation cycles. So we didn't recompile the code at all. What we did instead was we manipulated the bytecode. So this is really fast. You can do hundreds of thousands at least of changes to the bytecode in sub-second time. So this used to be called the generation cost. There's lots of academic research into how to scale mutation testing. A lot of it looks at the generation cost. We've made it go away completely by mutating bytecode. There's some downsides, but a lot of upsides. Catch me afterwards, we'll go through that one here. Second change, test prioritization. So we run the cheap tests first, we run the more expensive tests later on. And crucially, we stop as soon as one fails. So just by stopping, that would be half the time again. We're down to about half an hour. This first bit will sort of shift it to, I don't know, let's say 15 minutes by running the test, which is fastest first. If that fails, no need to run the more expensive test. But by far, the biggest sort of thing we've done, which makes it faster, is test selection. So the very first thing PiTest does when it runs is to gather line coverage, or block coverage. It does it per test. Then it only ever runs the tests against a mutant if on the same line of code as the mutant. Now this makes a huge difference. Imagine this code here. PiTest knows that that test executes just that one line. This test executes just those 2 lines. And this test here executes none of the lines we're currently interested in. So we had a mutant like this one on line 5. We only need to run 2 tests. Our test suite might have thousands of tests in. It might take hours to run. We need to run 2 tests, which maybe take a few milliseconds. In this case, the mutant's going to survive because we saw before we don't have an effective test case. The mutant here on line 6, we need to run 1 test only. Again, test suite could have millions of tests in. It could take days to run. We need to run only 1 test, which might take a few milliseconds. and that mutant, as we saw before, will be killed. We have an effective test case. But most excitingly, mutant on line 11 here, we have no line coverage, no block coverage. We have no test that could possibly kill this mutant. It cannot be killed. There's no way it can happen. So we can instantly mark it as surviving. We don't have to do any computational work at all. Now, compare this to something like Jester. This would be the most expensive mutant it could have. Jester would have to run the whole test suite to determine that this mutant here was surviving. So for Jester's most expensive mutant, for us, it's the cheapest we can have. It's a zero cost. Excuse me. So to analyze GOTO time, on my old laptop, it was about 8 minutes. This thing seemed to be a little bit faster. Quad-core workstation, about 3 minutes. So again, my maths is still a bit sketchy, but I think that's something like 1,000 times faster. We've made a step change difference. That's all great. First question people you ask me though is, yeah, that's fine. That's a tiny library and a small library. What about a big code base? What about my million-line corporate code base? Actually, it turns out that size doesn't matter. And to understand why it doesn't matter, we have to talk about what mutation testing is actually useful for and how to use it. So most of the research into mutation testing assumed it would work like this. Someone would write a bunch of code and possibly tests, depending on the era, and then they'd pass it to a QA team to go mutation test, some number of days, months, years later. So you have basically, all of a sudden, 2 million mutants generated right at the end. And when you talk about at a conference, most people assume it should be used like this. Run a bunch of code and tests, run overnight on a CI server. It's an expensive process. Of course it's going to go on a CI server. Where else would it be? And then afterwards, brag about the size of your metric or something. The crucial point being that you're not getting feedback until some sort of overnight run's happened, like the day later after you've written the code. I only have to use it like this. I write a family test, make it pass, mutation test, refactor. Actually, honestly, it's not quite like that. Usually it's a few tests and things, and then a mutation test, I don't know, every 20 failing tests or so. So not quite an inner loop, but right in there, happening all the time. Or sometimes like this. I hack out some awful code. I maybe sprinkle a few tests in, run PiTest, look at the awful mess I've made, and start to fix it. And actually, this works. I wouldn't dare do this without PiTest, in all honesty. It would be, I think, it would end badly. But with mutation testing, actually, I get an okay result. Probably not as good as I've test-driven it properly, but I get something faster, which sometimes is what I want. But the important point is, for both of these ways of working, I have to only analyze a very small part of the code base. I don't need to analyze 20 million lines of code. I need to analyze the code I've just touched, which will be 1 or 2 classes. And it doesn't matter how big the code base is. The size is always small. So interest with version control, not very clever, but usually I just say, I'm working on this bit here, I'll limit my analysis to these 10 or 20 packages, and it'll be fast enough to be able to do that. So it's a powerful tool. And the important word here is tool. I don't use it as a metric. I don't care what the code coverage of the project is. I don't care what the mutation score is. What I care about is the feedback I can get from mutation testing and what it tells me to do, and the actions it prompts me to take. Which brings us back finally to equivalent mutants. Now, the research suggests that it takes about 15 minutes to assess whether a mutant is equivalent or not. So a human being sat down for each mutant and saying, okay, missing test case, ooh, equivalent. So you can imagine back in the day when we did our big round of code and tests, over here, go do the QA team mutation testing. Here's 1 million mutants. That's an awful lot of work. It looks very impractical. But that figure itself assumes that you haven't just written the code. If I've just written some code, something tells me, oh, that's wrong. I look at it. It's quite a quick thing to assess. It doesn't take me 15 minutes. But it's much less effort when you do it regularly. But perhaps more importantly, it turns out when you do it all the time, these equivalent mutants actually provide useful feedback. So far from being just a problem, they're actually a side benefit of mutation testing. So if a mutant survives, I do one of 3 things. I add a test, pretty obvious, or sometimes fix a buggy test. I delete some code, which we'll talk about in a second, or re-express some code. These last 2 are usually in response to an equivalent mutant. Some examples. Here we have some code. Not very nice code, but it is code. And we've mutated, again, our greater than to greater than equal. Can anyone see the problem? Yeah, so we've got this ugly guard at the top. So I can never be 100 at that point. Simply, it's not possible. So the mutant's equivalent. But more importantly, the code is redundant. That code is to serve no purpose. So I can do this. This code is logically equivalent to the code before, but there's less of it, which is great because code is awful stuff. It's where bugs live. So we've made less code and have the same functionality. So it is good. So mutation testing is really good at highlighting redundant code. If its main purpose is to find sort of problems in your test suite, its secondary purpose is to find redundant code. It's excellent at it in a way that static analysis can never do. I think we saw this example before, where we're trying to calculate a minimum. So, okay, we've mutated it. It's equivalent. What do we do? This is classically logical equivalent mutant. This is like the purest form of equivalent mutant you can have. Well, we can make it go away, like this. So what we've done is we've taken that if statement and replaced it with something from Java standard library, math.min. And I prefer this code, because the code before worked, but it did what it did by doing it. This here expresses its intent. It's saying, I would like a minimum. The code now tells us that. It's more readable. It's very slightly smaller. And more importantly, that equivalent mutant has now vanished. So sometimes the mutants, when they're equivalent, prompt us to improve the code. Not always, but sometimes. And generally, it creates sort of pressure to reduce the amount of code you've got and reduce the amount of duplication you've got. Ooh, excuse me. So one sort of big class of equivalent mutants are ones that affect only performance. And these are equivalent because performance might be important, but it's not a concern of unit testing. You might have benchmarks and performance tests, but your unit test won't detect performance. So first question I ask when I have a mutant in some performance code is, okay, is this a premature optimization? Does it even make sense to be trying to make this code faster? If not, just delete the code. If it does make sense, ignore the mutant. And that's okay. You don't have to kill all the mutants. There's no need to kill all the mutants. You don't need some particular mutation score. It's feedback, and it's telling me, okay, there's something to look at here. You've looked at it. Your conclusion was, leave it be. That's fine. So let's see what we found in Google Truth. Well, first of all, some classic test errors. So this is primitive interarray subject. I believe it is for comparing two arrays of integers, and in this case, it's meant to throw an assertion error if you say these two things are not equal, and they are. Remember, it's a testing library for writing assertions. So PiTest took out this line of code. This is a line of code that actually throws the assertion, and no tests fail. So your assertion library doesn't have a test that confirms it actually throws assertions. This seems bad. Now, the mutant is covered by at least one test. This is a test I think was designed to cover that bit of code. First pass, it looks sort of all right to me. You can see it's putting two things in which are the same, and it's expecting this message at the other side. So, yeah, what's going on? Can anyone see the problem out of interest? Yes, exactly that. If you're doing this pattern, you need to have something here to throw in the event that this doesn't throw an assertion at all, which would mean it never hit the block down here. So elsewhere in the test suite, they're doing this. For whatever reason, this particular test missed out that bit of code. And also a nice equivalent mutation. Lots of code here, but I'll talk us through it. Same sort of thing as before, only this time for dealing with arrays of doubles. So look, PiTest took out this call here, which again is one that throws the assertion. And this time there was a test in place, which looked fine, didn't have that bug in, test looked okay. So what's going on? Why is this a surviving mutant? Well, the answer is down here. We have the same block of code repeated down here, because it turns out this actually is a performance optimization. So up the top, you see we've got this comparison for reference equality. So what it's doing is saying, here's two arrays. If they're the same thing, throw a message for assertion. If not, do some heavier work and then throw down there. Performance optimization, which isn't unit testable. And in this case, I think it makes sense. So it's a certain library, it gets an open-ended set of inputs. So you might be passing in really big double arrays in your code base, and it makes sense to optimize. So what do we do? Well, I don't like this method. I find it a bit big, a bit confusing, because I think it's doing more than one thing. Had a bit of a play, and changed it to this, which is really all it's done is it's split out the deep comparison into its own method. This rather clunkily named method here is doing the performance optimization and then the deep compare, and we just fail the once up here if either of those two fail. Equivalent mutant has gone away. I think the code is slightly nicer, and I imagine some in this code base must be an is equal to method, which is doing exactly the same down here with duplicate code. So we'll apply it, we can actually make the code base smaller. So the mutants prompted us to improve the code. There are other mutants here which would not be addressable in this fashion. If we were to mutate this to false, that would have to just live with because it's a poor optimization, but that's a longer talk. So actually often you'll encounter no equivalent mutants in your code. It seems to depend largely on sort of domain you're working in and sort of your style of coding. In fact, PiTest is designed to try and minimize the number that it generates. It can't guarantee it won't produce any, but the operators are designed so it's not too likely. So this is a powerful technique. It finds missing test cases. It finds buggy tests. And it finds a safety net for when you're refactoring your tests. And as I say again, it's the only thing out there which can do this. If you're not mutation testing, you're basically guessing if you've broken your tests when you refactor them. We've seen it highlights redundant code. And it can highlight code smells, as we've seen, with the equivalent mutants. So to be effective, run this as you develop. It's a development activity to be done as you're writing the code, not some number of hours, days, or weeks later. And also remember, it's a tool. So not a number to make go up. So you can use a metric. It's got some niche uses where you might want to use mutation testing to say, here's a number, that's a useful number. But for most of the time, you want to use it as a tool to give you feedback as you work. And importantly, not a stick to beat people with. I've introduced this to a few places now, and the first reaction is, I must kill the mutants, and you start to see the tests begin to become very coupled to the code, people are trying to kill the mutants. So it's a bad thing to set a target. I've talked a lot about Java, but there are systems of other languages. This is my curated list. So unfortunately, it tends to be quite a fun thing to work on. People get quite excited, they hear about it, they write their tool, and the really fun bit is making the mutants. Everyone goes and makes a tool to make the mutants. The bit where it integrates with the build tools, where it starts to scale, all these things are less fun and harder. So most of the tools out there tend to be sort of toys which aren't really fit for real-world use. This is a list of things which I either know or believe to be in the latter category of real-world usable tools. So Mutant for Ruby has been around for a long time now. Marcus, who makes this, he takes the equivalent mutant idea and really runs with it. He intentionally introduces them to force you to write your code in a certain style which is simplest. PHP has a good one. What's called Humbug, it's I think been rewritten as Infection. Java obviously has PiTest. There's also a tool called Major, which is an academic tool. It hasn't got the integrations. It's obviously designed for research mainly, but it seems like quite a solid tool. If you're writing Kotlin, you can use PiTest. So an advantage of using the bytecode rather than the source is, at least in theory, you can use any JVM language with PiTest. In practice, that isn't true. Something like Scala, you look at what the compiler produces, an awful lot of the bytecode doesn't map back to the source code. So I call these things junk mutations. For Scala, it's unusable. For Kotlin, by luck rather than design, the compiler produces things which actually work reasonably well. So I'm trying to make that a better experience. It'll be a little bit clunky still, but for first pass, Kotlin is mutation testable with PiTest. Python has a tool called Cosmic Ray. If you're on LLVM, there's a tool called Mull, which seems to be progressing very nicely. That's working with Swift and C and C++. Now, Strike is quite interesting. That's got quite a lot of traction recently. It's JavaScript, obviously. It's very exciting. I believe that actually the tool is also targeting other languages. I think there's a Scala version of Striker. I think also a .NET version now, which is good because .NET's been a little bit neglected when it comes to mutation testing. There have been a few tools, things like Ninja Turtles and Cream and a few others. They've all been abandoned, haven't worked particularly well, not really sort of got there. There's one called Fettle came out quite recently, which looks good. So that would be, if you're doing .NET, that'd be worth looking at, or trying the Striker.NET version. So I can't actually vouch for either of them, not actually use them, but they both look reasonable implementations. Which I think that is me. Please say I've actually not overrun, which I was going to do. This is my picture again. This is me on Twitter. Feel free to follow me. I've got like 2 followers, so I'm feeling kind of lonely. In fact, I might even stand at the door and do a room check on the way out. Make sure you are following. And I'm also meant to ask you all to remember to rate the session. But I think we actually have plenty of time for questions. Yeah.